Hello, this is part two of a fresh approach to teaching optimization from deterministic optimization to sequential decisions. Part two, we'll talk about sequential decision problems. Now, I'm going to start off by looking at what is very familiar to anybody who has a background in optimization. It's a static deterministic math program. On the left, maybe we're depicting the assignment of resources to tasks. On the right, this is the standard way that we write this out mathematically. It was a great breakthrough back in the 1950s. By the 1980s, we actually had software that was very practical, predominantly in the package originally Cplex that evolved into Groby. And what we will do is we'll sit down to this problem, run the algorithm, and then declare that the solution is optimal. Now, this is something that is done throughout the field of optimization. All of these books take this perspective of these optimization problems. So let's take this classic static deterministic optimization problem. Now, we'll recognize that we're not just solving this once, we're solving this over time, and this is my problem at time t. So I'm just going to go through and index everything by t to say, yes, this is the time t version of this problem. Now, what I'm going to do is I'm going to put an arg in front of this and say the argmin, that's the optimal solution x. So instead of getting the objective function, I just want the decision x. And we're going to call this a policy. A policy is a method of making decisions at a point in time. And I do this at a given state in the system. My state is the information in the A matrix, the B vector, and the C vector. Now, something that I often do when I'm optimizing over time is I may parameterize things. I may realize, oh, well, I'm going to have to make a decision now, but it may impact the future, and I'm going to put in various bonuses and penalties. For example, if I'm scheduling a machine and I have to schedule for a job in the future, and I think I know how long a job will take, but I want to put in a little bit of a buffer in case the machine takes longer or happens to break down. So there's a number of things that people in practice do. So I'm going to parameterize this. It's still a deterministic linear program or integer program if we like, but I've now parameterized it because in my ad hoc way, I'm going to try to make it work well over time. So here we're taking my initial data and we solve the problem. Now, new information will come in that gives me an updated state variable. That's the data that runs the linear program. I solve it again, and I keep solving it over time. Now, at each time t, I'm going to have a certain objective function. This is the cost that I've generated. This will be optimal at that point in time. But what really matters is how well I do over time. I need to sum these up. And the sum is the performance of the policy, which is the linear or integer program I keep solving over and over again. Now, I like to identify two objective functions here. On the left, we have what I will call a surrogate optimization problem. This is just used for making decisions. I don't actually care that much about this objective because any company is going to run this over time, and then they're going to say, how well did I work over time? I don't look at just my costs on Tuesday. I'm going to look at it, say, for the whole week or maybe the whole month. So the one on the right, that's actually the objective function that I want to do well with. This one on the left is just something that I'm doing because I do have to make decisions at every point in time. And yes, of course, I like to minimize those costs at time t, but I have to pay attention to the impact that it has on downstream problems. Now, what I have is the policy is a deterministic linear program. The function f is how I've parameterized it, and the thetas are any tunable parameters that I may have introduced. The objective function is the simulation of the policy over time. Now, the stochastic optimization problem is the one that says, what is the best objective function at time t, the surrogate optimization problem. Now, the f there would be how I've put in various bonuses and penalties. The theta is the exact values for those parameters. That is a stochastic optimization problem. So here I am doing deterministic linear or integer programming, but coming up with the right function to work well over time is a stochastic optimization problem. Now let's move on to what I'm going to call sequential decision problems. Let's go back to my wallpaper of various applications. Then we saw that we have a number of decisions that need to be made. Now, behind every one of these boxes, so put your eye on one of the boxes. Now I'm going to flip forward, and I've replaced it with the information that comes in after I've made the decision. Let me do that again. I'm going to go back, put your eye on a different box. Okay, pick out a box. Now I'm going to go forward. Here's the information that comes in after you've made that decision. Now, all of these are what I call sequential decision problems. Almost everything in human processes, because time always marches forward. So, for example, an inventory ordering problem, I place an order, maybe the inventory comes now or in the future, then I reveal the demands. Now I have to place more orders, so on and so forth. At my company, Optimal Dynamics, I'm assigning drivers to loads, but this happens over time as new loads are being called in. Maybe I'm in medicine and I have to be testing new vaccines and I have to decide what dosage or which people. Then I observe the various patient outcomes. And of course, there's finance where I'm buying and trading various investments while the market prices are changing over time. Now, the biggest challenge when making decisions under uncertainty is modeling. So with our deterministic problem, everybody around the world uses the same modeling vocabulary. And so that really makes things much easier. This is also true for machine learning. However, when we lack a standard modeling framework for sequential decisions, we get to what I like to call the jungle of stochastic optimization. Every one of these phrases is actually a distinct community. Behind every one of these communities is one, maybe a whole series of books. There's 8 different notational systems. There's a variety of various techniques that people use. I'm going to propose a modeling approach that fits here on a single PowerPoint slide. So our state variable st is whatever we know or believe. So for example, in my linear program, I use the letter st to designate the matrix A, the vectors B and C. This is whatever you know, but it can be estimates of something you only know imperfectly. X is the decision. It can be scalar or a vector. Now wt plus 1, that's the new information coming in that I didn't know when I made the decision. Now, each time we make a decision, we have some performance metrics, a cost or a contribution. Now, decisions are made with a method that I'm going to call a policy, which we design later. Now, this is the point of departure of my new approach versus all of those other books, one of which was mine. I'm going to propose this function and say we will design this later. It's just like deterministic math program where I formulate the math program using an X that I don't know, and then I put together the model, and then I have to have algorithms that go find X. Now the unknown is the function, which is the policy. I'll come back to that. Now, as we evolve forward in time, we're going to use something that's known as the transition function. This is very common for people with an optimal control background. You're in a state st, which is what you know or believe. You make a decision, then you observe the new information. The transition function says, oh, here's your new state variable. Now, eventually, the goal is to find the policy that maximizes contributions. So for deterministic problems, that's fairly clean. Now, here I'm going to take that previous slide and put exactly that same information into 5 components: state variables, decision variables, exogenous information, transition function, objective function. Now, this is inspired by deterministic math programming where you have decision variables, objective, and constraints. It's just a little bit richer. Now, these 5 components, I can model any one of the problems on the right-hand side. In fact, any sequential decision problem. I might add that a static problem is just a special case. I can cover any of the books in the jungle. This is why I call it the universal modeling framework. And if you look at this for a while, I hope you can look at this and say, okay, wait a minute, this is a little obvious. He's not actually doing anything here. However, this is not standard. The standard approach for deterministic optimization is standard. Everybody writes it the same way. This is not standard in the world of sequential decision problems. You can find an example that field of optimal control will use this, but mainly for deterministic problems. The rest of these use various other ways of writing down the problem. Now, In the world of sequential, objective functions are a little bit more interesting. We might want to optimize the cumulative reward, and this is normally what we call online learning. Or we may run a bunch of experiments, and all I care about is how well I do at the end. We call that the final reward. And maybe I want to introduce a risk metric. However, in all of these, I'm still searching over policies. Okay. Now, uh, the objective function, let's say we're going to use the online version of it, it's conditioned on S0. That's the initial state variable. This is the information that I start with. Now, R0, that's the physical side. That's my inventories and people and equipment and whatnot. I0 is what I call other information. This is parameters and anything that I might know perfectly, because B0 contains beliefs, forecasts, market response, arrival times, yield. This is what I don't know perfectly. Now, these three sets of variables, this is the state of the world. Now, state variables, this is the initial state that drives the whole system. Now, evaluating it, there's three ways of evaluating a policy. One is theoretically. There are very simple problems where I can sit down and prove theorems and say, okay, this is how well the policy works. It doesn't happen very often. Now, often I may want to go to a computer simulation. So I code this up and I simulate it. This is what I would do as an academic. This is a powerful strategy for certain classes of problems. However, the vast majority of times, we do it in the field. Okay, the field is always a simulation. Now, what I want to do is search over policies. I want to find the best policy. Now, the search over F is typically done by a human, although I'm starting to see evidence of people trying to do these with large language models. Then we have the tunable parameters, which is always done by some sort of an algorithm, maybe derivative based, more often derivative free. Now, how to evaluate a policy, you might say, well, I just want the one that works the best. It's not that simple. Of course, we care about solution quality, how well it does on average, but I may also want to look at the worst case performance or some form of risk measure. But that's not enough. Computational requirements, the speed and the reliability. For example, yes, it normally takes 5 minutes, but does it sometimes take 30 minutes? Transparency. When it comes back with an answer, I may want to say, well, wait a minute, how did it get this conclusion? Sometimes transparency is a dominating factor. Methodological complexity. You're a decision analyst at a company and you've got to code this up. Some of these algorithms are very hard to code. And they're fairly high risk. And then there's the data requirements. So when we go to choose a policy, it's a little bit more complicated than deterministic optimization where we just want the best X. Here we need a good function that works well in multiple dimensions. Okay, this is the end of part 2. Again, this URL is a resources web page for sequential decision analytics.